Okay, I have to continue the lecture. So we have another part that we haven't talked about. So if you already know something about radiation, then you can keep on doing your tutorial. Okay, it's fine. Okay, so the next part would be about the radiative transfer. So before we talk about that, so it's one kind of the heat transfer. If you haven't studied physics before, this would be helpful. Okay, so we have a so-called black body. So what defines a black body? A black body would receive all the radiation hitting this black body, and then the energy would be re-radiated back. So it accepts all the incident radiation and it emits all possible radiation. Okay, and the Earth is treated as a black body. So which means that we receive energy from the Earth and then we radiate that back to space. Okay. So we try to, so on Earth, the Mother Nature tries to keep the temperature the same. So we hope that the energy we receive, we will radiate that back to space. Okay, so that our temperature would not be increasing or decreasing. Okay, that's the whole idea. Okay, but there is something that we should know about, is that the Earth and the Sun, they have different temperatures. Okay, so if they have different temperatures, they will radiate at a different frequency or at different wavelength. Okay, here I'm showing you the so-called spectrum of the things that radiate at different temperature. Okay, 250K, 300K, and 350K. So for all the black body, they radiate at all frequency and all wavelength. Okay, so here I'm just showing you the graph of wavelength. For example, this 250 degree Kelvin, it radiates at all wavelength. But there would be like a maximum intensity, right? The maximum intensity for this lower temperature would be higher wavelength. Okay, and the maximum intensity would be at a lower wavelength. So somehow it's related to how strong your radiation is. Okay, so lower temperature radiates higher intensity at larger wavelength. So what is wavelength? So if you haven't studied that before, so if this is the wave, I think all of you have studied sine or cosine before, right, in your high school. Okay, so if this is the wave, the size of one cycle, the length of one cycle is wavelength. So for light, we sometimes consider light as a wave, as a type of wave. Okay, so we have some equations to describe that. Why do we study this? Because it's related to the energy that we receive or radiate back. Okay, so we sometimes consider the EM waves or the visible light. So light is one kind of EM wave. So we have a spectrum here. So different wavelength is referring to different things. So this is your everyday life terms in here, right? Microwave, infrared wave, visible light, ultraviolet, and X-rays, they are all electromagnetic waves, okay? And they are characterized by the wavelength on the left-hand side here, okay? So it means that if we put this wavelength back to the equation, so at speed of light is constant, okay? So we can get the frequency back. Okay, so these two terms, we can use them to characterize which type of EM waves that we are talking about on the left-hand side here. Okay, and speed of light doesn't change. Okay, so now we have, for example, if we are speaking about visible light, so the range here is here, right? That's 0.7 micron, between 0.7 micron and 0.4 micron. Okay, between these two. That would be, why is it called visible light? It's visible to human beings only. Okay, some other organisms, they might be able to see infrared. Maybe some of them can see ultraviolet. but only if the visible part is visible to human being. Okay, so if we substitute this number, the wavelength, back to this equation, we can calculate the frequency. Okay, and if we have the frequency here, we can put this back, this new parameter, and H is a constant. It's called Planck's constant. Okay, we can calculate the energy. Okay, which means that the wavelength is very much related to the energy that we are receiving. So just by looking at the terms here, microwave, infrared wave, X-rays, ultraviolet, you already have some common sense, right? Which one is very, very dangerous? Of course, X-rays, right? Why is it dangerous? Microwave, probably, it sounds like something very safe, right? You use that in your house, right? You use that to heat up your food, right? So it has a higher wavelength, right? Higher wavelength, which means it has a lower frequency. So lower frequency, lower amount of energy. So that's what it means in this equation, right? The bottom equation, okay? So this slide is for your revision. I'm not planning to go into details to talk about waves. Okay, so it turns out that we have an equation which is called Planck's law, E here, describing the number on the curves in here. Okay, for each of the curves, you can substitute the temperature back to the equation T in here, and C1 and C2 are two constants. Okay, lambda is the number on the x-axis. Okay, so if you have two variables, one is the wavelength, the other one is the temperature, you can find the value on the curves, which is the intensity. Okay, but we usually don't need to calculate this one. So this is just giving you some idea what we are looking at in terms of the environment, right? This is environmental engineering. Why do we care about this? Because we are receiving solar energy every single day. If you want to make a solar panel system very efficient, then you need to know how much energy we are receiving, right? So here, the orange part is the solar radiation, which is the visible part in here, okay? And the light orange part here is called the long wave radiation. So it's radiating from the Earth. So they have different colors, okay? Why do we care about this? Because this is the part where we get the greenhouse effect. So our atmosphere is trapping this part of the energy, okay? So on the left-hand side, it's solar radiation, so visible light. On the right-hand side is radiation coming from the Earth, probably the infrared part. So higher wave number, lower amount of energy or lower frequency. Okay. So this issue is highly related to the global warming problem, to the climate change problem. So on the left-hand side, I'm showing you the heart of the problem. The heart of the problem would be carbon dioxide, right? So here I'm showing you 1C CO2, so two O's in here. So this is the structure of the carbon dioxide. So you would ask the question, why our atmosphere is absorbing, or why the CO2 is absorbing this part, but not the solar radiation part, right? On the right-hand side, it's the radiation coming from the Earth. So this part is being trapped, okay, not this part. Why does it have like a selective property? So it's due to the different vibrational mode of the CO2. If they are vibrating at a different modes in here, so it's like having two arms and it could move different ways. So I have some arrows here showing you that different ways. So different modes in here, they absorb at different frequency or different wavelength. Okay, that's what it means. Okay, so we are now having some measuring devices at the star locations in here, right? Reaching the Earth. So you are measuring how much energy is absorbed by the atmosphere for the solar radiation. And here we are measuring how much energy is absorbed in the radiation by the Earth, right? The blue arrow is showing you the radiation from the Earth. So if we do measurement in here, you will see how much is absorbed, right? So for the red arrow here, if you do measurement on the surface of the Earth, you will see how much is absorbed, right? The light is going through all the layers of the atmosphere, right? So this is what I will be showing you in the next slide. So here, on the left-hand side, the red one is the spectrum for the sun. On the right-hand side is the spectrum for the Earth. So you can see that comparing, so the shaded area is the measurement, okay? The shaded area is the measurement. And the curves are the theoretical curves, which is coming from the equation. So whenever we compare these two, we'll be able to see which part is absorbed. Okay, for the red one, we are measuring at the surface of the Earth, right? So you can see that our atmosphere is not totally 100% transparent to solar radiation. Some part of it is absorbed. You can see that at a certain wavelength, here, right? The white areas, they are absorbed. So if you look at the graphs on the bottom, you can see which kind of greenhouse gas is doing the absorption. For example, this one, this dip in here, water vapor is doing a lot, right? Water vapor is doing the absorption, right? So, but mostly it's transparent. So if you compare the curve and the shaded area, they are almost the same. I know that it doesn't look like it's almost the same, but in reality, it's very hard to find something which is very much matching with the theory, actually. So this is already matching very much. On the right-hand side, you can see that just a part of it, of the radiation coming from the Earth, can go into space. Okay, a large chunk of it is absorbed by our atmosphere. Okay, so which part is absorbed by which part, which wavelength is absorbed by which wavelength. You can see that a large part of it is actually absorbed by water vapor, okay, here. And another large part is absorbed by carbon dioxide. So that's why we're saying that carbon dioxide is the most prominent greenhouse gas, because it's doing a lot. The amount of carbon dioxide probably is much more than the water vapor. So that's why we care about this very much. And we have other greenhouse gases like methane here. So this is the peak. So it's absorbing the range referring to a certain wave number in here. So now if you look at these two, compare these two, you know that our atmosphere is not transparent to the radiation coming from the Earth. Okay. Okay, so if we do measurement, so the black curve in here is from the equation, which is the theory. Okay, and the orange one is the sunlight at the top of the atmosphere. So the orange shaded region, you put some measuring device on the top of the atmosphere. So probably at the end of this arrow, right? At the back of this arrow. This is the orange one. Okay, and then what would be the red one is the radiation at sea level. So this star, okay, probably this star. The radiation at sea level, so a part of it, of course, some part of it is absorbed by the atmosphere, but you can see that for all the wave number, it's there is a decrease, right? For all the wave number, there's a decrease. So this is normal, right? If the light is going through some media, some energy is lost, but there is some part for some wavelength is more absorbed, right? So this is just repeating what we had for the red graph in here. Okay, so if you look at the spectrum for 10 meters below ocean surface, is even more. So that's why in the ocean, it's very hard for the plants to get the sunlight because it's absorbed by the water. The energy is absorbed by the water. Okay, so this is like a blow up graph for the one on the left-hand side in here. Okay. Okay, so what do we actually care about? We don't care about the actual numbers on the black curve, but we care about the area under the curve. So if we do integration, the area under the curve, we would calculate the total energy. Okay, the total energy, but you don't need to do the calculus in this course. So you just substitute the temperature into the equation. And A is just the surface area of the object, okay? And this one is just constant, Stefan-Boltzmann constant, okay? Which means that if you have the area and the temperature, you can calculate the energy, total energy radiating from a black body, okay? Okay, so the area, total area under the curve. Okay, and another thing that we might be carrying is this Wend's displacement rule. So it's calculating the peak of each of the curves in here. You will have to do homework for this part. So don't say that I didn't teach this part. Okay, so for the peak of the curve, sometimes we want to know the wave number. So you can see that as the temperature decreases, the wave number increases. The red one is showing you the maximum location, right, for each of the curves. Okay, this is calculating that. If you plug in the temperature in here, you'll be able to calculate the wave number at each of the peaks. Okay, so here is an example showing you how we could use this Stefan-Boltzmann law. So consider the Earth to be a black body, average temperature 15 degrees Celsius, and we have a surface area. And we find the rate at which energy is radiated. So we plug in the temperature and the area, right? It's given, they are both given to you. So this is the energy radiating from the Earth, total energy radiating from the Earth. Okay, and the next part of the question is compare the peak wavelength. So just plug in this equation, Wend's displacement law, plug in the temperature. So the temperature of the Earth is 15 degrees Celsius. And for the sun, it's given to you 5,800 Kelvin degree. Okay, much higher energy. You can see that the wave number is much smaller. Frequency is much higher. Okay, that's it for this lecture. Okay, let me know if you have questions.